So there's been a lot of talks about batteries. Our batteries are contained in stainless steel containers. We make them fireproof, meaning if something goes wrong inside, the fire stays contained inside the enclosure. Of course, we can also extinguish fire on a modular base with non-conductive fluid. This is what happened just now. That was a thermal runaway. You have seen the reaction that it injected, and you have seen the amount of smoke that happened. This is a 153 amp hour NMC battery cell. It's really boring because nothing happens, and that's what we want. Now, what is the next stage? What you can see here, this is the solid state battery that we are now just certifying with DNV. Here we can punch a nail through it 5 millimeters and nothing happens. We might have a little bit of smoke, but that's about it. So in order to go into a thermal runaway with them, we need to inject a glowing stick, so a glowing 6 millimeter rod, and then we manage to get the fire or smoke, which is very limited. So the safety leap is just tremendous up, so we don't need to inject water here. We don't have cell-to-cell propagation. We don't need all those barriers that some of them have talked about earlier today. As we can have cell by cell, one goes into thermal runaway, the other one does not. With the solid state technology, we go up to 350 degrees and it does not self-ignite. We love this because it keeps design very simple, and we love a simple design. It also makes it more price economic. Here you can see solid state, or it's half solid state today, yes, battery tests that we did. If any of you have done LFP tests, which is considered by some companies as the safest battery technology, that's the amount of smoke that we get out of the solid state in a thermal runaway. If you have an LFP battery, this is about 1.5 meters, you will see a rocket steam of smoke that is at least 4 to 5 meters high. We can overcharge this battery with a factor of 6 to the max cell voltage, so we can go to 20 volt, nothing happens. So we can almost say the BMS could be obsolete. We can short circuit them, we can put them into a deep discharge of 0 volt, nothing happens. We can puncture them, nothing happens, so only with the glowing stick. It's really a next stage. Plus, they go up to 8,000 to 10,000 charge cycles, depending on the DOD that we do, which is also, based on invested money and materials, very economic. Now, where does the battery industry take us? We have very good contact with our cell providers, so a little outlook in the crystal ball. We are now around here, 25. So we have half solid states based on NMC technology going up to 310 watt hours per kilo. There's two sorts of solid state technologies today, or half solid state. One is based on NMC technology and the other one is based on LFP. On the LFP we have very long, very good cycle life, up to 10,000, 12,000. On the NMC based one we have up to 2,000, 3,000. So that's the big difference. It comes at the price. Here we can see 310 watt hour per kilogram. So it's more for speedboats that don't make so many cycles. And here we have half solid state LFP at 190 watt hour per kilogram. Now we're coming into next year's prediction. We're going up to 330, 250 watt hour per kilogram. And in 2028, we will start talking about the real solid state. I have to be honest though, but that this date has tended to shift a little bit backward over the years. So I have modified this graph. I'm using the same graph every year. But we're going up to here to 450 and 500 watt hours per kilogram, which is then really starting to be a game changer.